All right, cool. So welcome to our final tutorial. I hope you've learned a lot this course. Today we'll be covering unsupervised learning. Just a bit about that. So I'll go through the lecture notes and then the Jupyter notebooks as per usual. I've uploaded the Jupyter notebook answers into our team's file sharing facility as per normal. Let's get started. If you're wondering about the haircut, it's the whole COVID-19 situation. I just cut it myself. Didn't want to go to the hairdresser, so hence all the hair being gone. Anyways, it is what it is. Cool. So unsupervised learning. So what's this all about? In a nutshell, supervised learning just means that you have a target or a response, and unsupervised learning is just you've kind of just got a cluster of data. There's nothing in particular there might be things you're interested in, but there's nothing in particular you're necessarily trying to predict, or maybe there is, but you don't have that field, or it's not available to you. And we're going to explore today a variety of use cases. I'm actually doing a bit at work right now. Finally, a bit of a coincidence that we're talking about unsupervised learning. Cool. So some of the things that we'll be talking about. So as saying here, so supervised learning, the classes are known, or it might not just be the classes. It could just be if it's a regression exercise, it will be the number of some sort. It could be a real number, some sort of numeric value. It's known, the target's known, so it doesn't have to be necessarily a class. It could be a regression exercise where it's a number. Cool. Unsupervised learning, the classes are initially unknown and need to be discovered. So we're not given a target, we're not given a response, and it could be we're trying to find some class, we're trying to extract some sort of information from our data set. Right. Okay. So why do we need unsupervised learning? Most of the world's data is unlabeled. So I guess it depends on where you end up, working out. But there's quite a few examples of places where there's not necessarily a label. So off the top of my head, potentially some recommender systems that you might see, when you're going online, they recommend products to you. Some of that they'll feed. I mean, something on Amazon or whatever would be very, very complicated. But I imagine there'll be something unsupervised feeding into that. We're just clustering segments of customers together. You're with this sort of customer. You're like this sort of. You're similar to this sort of cluster of customers. So perhaps you'd be interested in buying these products, that sort of thing. So getting human label data is expensive, difficult, time-consuming. Yep. Other interesting uses. So aside from, I guess, you use it a variety of different ways. I mean, you've got your, I guess, say I mentioned the customer segmentation, for example. You could use it as some sort of, I think I mentioned EDA or exploratory data analysis before. So it's something you do or something you theoretically do before you start modeling your data, just to get a feel of what's going on. And part of that could be doing some clustering, some unsupervised learning to sort of understand your data better, to see if there's certain segments that are of interest. They can maybe model a different way, or flesh out, or explore, see what's going on. There's other things as well. So did I talk about dimensionality reduction? I think we'll talk about it a bit later. But another use case is dimensionality reduction. And so by that I mean essentially reducing the number of columns. So if you're performing some sort of modeling, let's say on tabular data, I think that's the kind of data that I'm most familiar with, and I also think it's easiest to understand. If you're dealing with tabular data, and it could be that you have many columns. You could have many thousands, right? And for whatever reason, there could be a variety of reasons you want to squish down the number of columns, right? One of it could be that you want a simple model, and that could be for not a simple model. One of it could be that you want less features for your model to deal with. Depending on how you going about doing the modeling process, it could be a bit of an iterative process where there's a bit of judgment from the modeler, trying to work out, should I add this feature, remove this feature, should I, they might be going through each of the features, almost one by one, or, and if there's thousands of features, you really don't want to deal with that. That's far too many to deal with. So and another case might be for noise reduction, right? It could be, and we'll see some examples of that later today. We find sometimes these clustering algorithms that they help break through the noise. If you have so many columns, it helps break through the noise, sort of simplifies it and boils it down to, I guess, the underlying construct you're trying to measure. And other times it can help you understand the data, right? So oftentimes you could have columns that are highly correlated, right? And that's not good. When you have correlated / redundant features or columns, it's not a great thing. It can add variance to your final estimate, and the model can find it a bit trickier to fit to that data set. So these clustering, a lot of these clustering algorithms that we talk about can help cut through that quite a bit. Cool. Okay, for EDA. Yeah. The other thing to note about unsupervised learning is that it can be a bit less clear cut as to whether you did a good job or a bad job. It could be a bit more subjective. There are some measures that people have proposed, and there's some silhouette plots that are talked about in the lectures, but in general it's kind of harder. Unlike you imagine in a regression task where you have just say your root square mean error, your mean square error, or maybe you've got say a Gini coefficient or ROC, AUC for classification or accuracy, where there's a clear objective measure of how your model's performing. It's a bit harder with unsupervised learning. Now, when the dimensionality is smaller, it can be a bit easier. You can just visually have a look and see if the clustering makes sense. So in a lot of the examples we see in the lecture slides, as well as in the Jupyter notebook, the dimensionality is kind of smaller, so it's okay. You can just have a look visually and just judgmentally work out if the clustering was good or not. Okay. And there's a bunch of different ways you can look at clustering. So this is a sort of a hard margin, sort of a hard clustering, so it's either in one or the other. You can also have a more soft clustering. So hard clustering would be things like k-means would be a hard clustering method, so it's either in one or the other. You can also view it from a probabilistic point of view. So for example here, these observations, and 1, 2, 3, that's 3 clusters. And we'll look at it a bit later, but say if you use your Gaussian mixture models, you get a probability of being in each cluster rather than a hard sort of classification. Now, of course, if you had to choose one, you'd probably choose one with the highest probability. So, for example, with observation A, I'd say, okay, it's in cluster 3 because it's at least this model is saying it's most likely to be in cluster 3. This is sort of what we say a soft clustering approach, such as the Gaussian mixture models, which we'll also see. And then there's also a Dendogram. There's another way of representing. So there's different ways to look at these clusters. And the Dendogram, it can be a bit funny to look at. I think it's quite popular in microbiology / biostatistics. I don't know anything about it, but I hear it's quite popular there. Looking at genomes and stuff. But the way to interpret this is, you start from, let's say, look, these are all individual observations. And what will happen is, at least from the bottom-up approach, which we'll talk about a bit later, is you pair up and group together the guys that are the most similar, and then they'll form their own cluster. So let's say, if you're at sort of this level of clustering, you have 1, 2, 3, 4, 5, 6. Ooh, hope that's not affecting it. That's all right, I'll be on YouTube later. So if the quality isn't great now, I'll upload to YouTube later. So they'll be at 1080p, 60 FPS. Not that we need that many frames per second, but it's there. So if the network quality isn't great, it'll improve later on. Let me actually have a look. What's going on? Isn't my... No, it's not my VPN. Yeah, that's a bit slower than normal. I think it's just peak hour. I mean, everyone's at home these days, so you know, the networks are kind of, the bandwidth is kind of choked a bit. You know, that looks okay. I think that should be fine. I mean, well, let me know if you get any network issues, but I don't know what I can do about it, other than just say go on YouTube afterwards. Cool. Yeah, so sorry, as I was saying, Dendogram is another way of looking at this clustering. So at, say, this level of clustering, you know, you have 1, 2, 3, 4, 5, 6. You have 6 clusters, right? And you know, you can sort of choose how, I guess, granular you want your clustering approach to be with all these things that we're going to talk about. So just even with this Dendogram, you can have it like super granular, maybe at, you know, say this level. Sorry, actually maybe at, say, this level, where there's, you know, 1, 2, 3, 4, 5, 6, or you could, you know, go even more, or go, you know, you could get to a less granular level. And if you say at here, you'd have, you know, 1, 2, 3, 4 clusters, and you can go up and down. I hope you get the drift, but you know, when you look at the Dendogram, how high and low you sort of look at, you know, you start looking at it reflects how granular your clustering is. And of course, with something like this, if you're using k-means, that parameter, the k, can be adjusted to sort of work out how many clusters you have. And we'll talk a bit later about how you go about choosing that, the k, or the number of clusters. Cool. So yeah, so with your hierarchical clustering, there's 2 ways. You can either you know, go divisive, top down, or agglomerative. The way I think of it is, you know, to me, agglomerative sounds like a bit of a glob. So you kind of just glob things together. It's probably a bad mnemonic, but that's how I remember it. Divisive, you cut things down from, you know, you have to start with one big cluster, you keep cutting. So hopefully that kind of makes sense as to which one's which. Okay. What should I talk about? Yeah, so an important concept here is your similarity matrix. Where is it? Yeah, here it is. Yeah, your similarity matrix, or I guess you could look at the opposite side, the other side of the coin, your dissimilarity matrix. And you can measure these a couple of different ways. You know, if you're doing a similarity matrix, you could use something like correlation. If you're using a dissimilarity matrix, you could use something like distance, you know, of various forms, L1, L2, L3, whatever, what have you. Euclidean or L2 might be the most common metric. But either way, you know, the 2 sides of the same coin, so just adjust the algorithm accordingly. You know, if you're grouping things together, typically you want to minimize a dissimilarity or maximize a similarity. So you just got to be careful about which one to use, whether to maximize and minimize, depending on whether you're using a similarity or dissimilarity matrix. Cool. Now there's one concept. So in general, with your clustering, so no matter what method you're using, there's 2 things you kind of want to do. You want to minimize your intra cluster variation. Now, when I say intra cluster variation means the amount of variation, you know, within, right? So intra cluster variation. Maybe I'll write this out. It's kind of. Oh, I don't like how it's in Mac. Alright, so let's open up the Windows version. So the intra, TRA, is within, so within a cluster. Inter is between. The way I remember it is, you know, you think, okay, I want to go interstate for holidays, so that's going to a different state. So inter is the different, you know, between different ones. Intra is within, right? So sorry, it's a bit slow. I don't know why everyone goes on about MacBook Pros, because I don't really find them that fast. My Windows computer is a lot faster, significantly faster. I don't want this one. This guy. Alright, maybe I'll do this one. Cool. So intra cluster, inter cluster. Okay. So when we're doing our clustering, we essentially this is we want to minimize this, right? We want everything in the same cluster to be similar, right? And on the flip side, inter-cluster variation, we want to maximize this. We want things from different clusters to be very different. Okay. Now, so looking based on that definition, based on these two things that we like to see in good clustering, we can see why this is a bad clustering, right? Why this is bad clustering, right? Each circle is a clustering, so you can see there's a small distance between points in separate clusters. So the inter-cluster variation is quite low, so you can see, look, it's right next to each other. That's not good. And on the flip side, there's a large, and the other part of it is that there's a large distance between points in the same cluster. So the intra-cluster variation is quite high, which is bad. We don't want this. There's a good cluster. This is good clustering. So you can see the inter-cluster variation, the distance from here to here is bigger. And you know, within here it's a bit smaller. Let me see if I can make my mouse a bit bigger. Pointer. It's here. So I'm just going to try and make my mouse a bit bigger so it's easier to see. Where is the pointer? Mouse pointer. I would have thought it'd be in here, but I don't really see it. Okay, look, it doesn't. It's no big deal. Alright, okay. So we can see how this is a good clustering. Okay. So the first clustering method that we'll talk about is your k-means clustering. It's also the simplest and not relatively easier to code up and also understand, I think. Now, before we go into it, let's go here. So what k-means does is you specify k, say 2. In this case, you know, feels like 2 is a good one. We can visually see that there should be 2 clusters. And the k-means algorithm will go through and find, you know, 2, I guess, centroids, right? 2 middles of both of your your clusters, and it will do it in a way that effectively minimizes the intra cluster variation, right? There's a few problems that we'll talk about later, namely around being stuck in local optima, as well as, you know, how to find the number of k. But let's go through the algorithm a bit first. So effectively what you do is maybe I'll talk to this first. Effectively what you do is you go through each of your data points, and then you initialize, you specify k, let's say 2, and then you initialize both those clusters to 2 random points within your data set. So it could be, say, this guy here and say this guy here, okay? And then you go through your data, and then you assign each of these data points to their closest cluster, right? So we had this guy and we had this guy, right? So then you go through and you go through all the data points and you assign them to one of the clusters, okay? And then you have a clustering. Now you will re-update your centroid, or re-update the center of the cluster based on your new guys, right? Or based on everything you've classified into both of the respective clusters. So then, let's say you started here. The example I was talking about, you know, let's say I had this as one of the clusters and this guy as one of the other cluster. You know, I should probably draw this. Hey, screen. Does this? Ooh, will this? No, I'm scared it'll break my screen recording. Let's, can I use this one? Can I take it on top of here? Maybe it will work. Okay, hopefully this doesn't stuff up my recording. I'll be very annoyed if it does. Okay, just like the bullshit. Okay, no, it's still recording. Okay, I think we're in business. Now let me open up Paint. Okay, so with the k-means algorithm, let's say we have cluster 1. So here we go. So this is our cluster 1, right? I'm gonna call it C1. And then we have cluster 2. Let's say this guy here, C2. C2. Okay. So you step 1, you initialize your clustering to something random, and after this, you go to all your data points. You're like, okay, cool. Where, which one of these would the clusters be? Would each of these points be closest to? So you go through them all, and it feels like, I feel like the dividing line's probably somewhere around. Yeah, it's here, isn't it? Yeah. So all these guys would be assigned to cluster 2, and all of these guys would be assigned to cluster 1. Okay. So after you do this, then you will reevaluate your clustering. So you go through and okay, cool. Let me go to cluster 1 and say, okay, let's recalculate the centroid. What's in the middle? What's in the middle of all this? So the middle of all this is probably, I'm gonna just approximate. It should be somewhere around here, right? Now in practice, what you actually do is you go through each of the dimensions and average it out. Now, when I say each of the dimensions, what I mean to say is, this guy here is, let's say the this guy here is say x1, and this guy here is say x2. What you do is, for all of these points in cluster 1, you'd look at the average of all the x1 values, okay? And then for all of the points in cluster 1, the blue cluster, you look at the average of all the x2 values, right? And then this will be the new clustering here, this blue circle right over here. And then you do the same for this guy here, and maybe this is your new clustering, okay? Now after you do this, then you recalculate what the clustering is. Sorry, after you recalculate 2 centroids, you go through your data set again and work out who it's closest to. Now this is when I realize it's probably a bad example, because I don't think anything really changes. in one iteration, we've basically landed at the we want to end up anyways. But you can imagine if you recalculate the centroid. So it's the centroid has gone from here. It's moved from here to here. Oh geez, I want to brush down. It's moved from, this was the original clustering. It's moved to there, and it might shift slightly over there as actually wouldn't shift. And then they'll just but let's say the data points change in clustering, then it'll shift, right? But visually, this is what's happening with your k-means algorithm. I should have chosen a better example, which will take a few iterations, but we'll see in the lecture slides. Cool. So let's step through this. So you choose random centers, your centroids at random, and then you go through your data set one by one, and you assign each of the clusters. Then you recalculate your clustering based on whoever has been assigned to each of the clusters, and you repeat until convergence. Now convergence means the clustering doesn't change. So in my bad example that I drew up here, it would effectively have converged, because once this blue cluster moves over there, and once this green cluster moves over here, it's not changing. I mean, none of these dot points change. I mean, these will still be green, these will still be blue, and it's kind of settled. That's it. This is converged, which is always a bad example. Okay, cool. So what's happening here is your k-means is minimizing the intra-cluster variation. This is the intra-cluster variation. I'll step through every bit of this formula. So I is the data point number, right? So let's say you have n data points. It goes from I all the way to n. This is d. It's just some sort of distance function or dissimilarity function, right? So this is the distance from, say, I, the ith observation, and this just tells you which cluster it's been assigned to. So the distance from all your data points to the respective cluster that they've been assigned to, and the k-means will try to minimize that. So it's using something called expectation maximization. So if you are curious, there's a YouTube video I saw a while back which I think explains it quite clearly, but we'll walk through it in the context of your k-means. The same thing, isn't it? Feature vector. Yeah, we'll walk through in the Jupyter notebook. Okay, so this is probably a better example because you can see the clustering changing, and at each iteration. So your starting point was over here. Actually, maybe I'll take a screenshot. Probably easy to see, isn't it? Okay, I'll draw on blue. Wow, paint is lagging. That is not good. Oh no, it's not lagging. Right. So you've got your clustering here. This is where k is equal to 3. So you have 3 clusters. Now, your starting points are here. So your initial centroids are here, here, and here, and you can see they move with each iteration. In this case, we've got 3 iterations until it's stabilized. So initialize it at some random points, say here, and then let's say in the initial one, this is the boundary, isn't it? This guy here. So let's say for this clustering, everything in here belongs to this cluster. Everything in here belongs to this cluster, and everything in here belongs to, actually sorry, I'm not looking at the lines right, am I? Sorry, everything here, let me start again. Everything here belongs to that cluster, everything here belongs to that cluster, and everything here belongs to this cluster, okay? And then you recalculate the centroid, and after recalculating the centroid, okay, actually, if I average out all these data points here, it's going to move to down here. And now, actually, it's everything. Now, after move down here, sorry, it's not that one, is it? This one. Okay, so after moving from the initial purple clustering to green, which is the second one, so this one is the initial clustering, I'll say. Initial clustering. And then we go here. And then this is the, I guess this is the first iteration. Okay, and then hopefully you can see, your clustering goes from the initial to the first iteration, and then all the guys here, everyone here, belongs to this cluster. And then you recalculate and you keep going until it's stabilized. this is more of the same. More of the same. Cool. Here's a question. How do we go about choosing the number, the k, the number of clusters? Well, that's a couple of different ways. If it's is it Control Shift? Oh no. What is the shortcut for new slide? So choosing number of clusters. So it's a couple of different ways you can go about doing it. You know, we'll talk about an elbow plot a bit later. So you can use percentage variance explain. You can use, say, the elbow plot. You can maybe do it visually, and other things like silhouette plots and then other metrics. So the question is how we choose a number of clusters. Now this applies to any clustering algorithm. So for something like k-means, this is just k. For something like PCA, this is the number of principal components. So I'm actually going through this exercise at work, actually doing some PCA, and we're doing it for dimensionality reduction. The data set which has 16,000 columns, which you can't use because it's too big. And actually the way we're going about choosing the number of principal components is we're using a combination of these two really. The elbow plot, which I'll show a bit later, is kind of a point where you see the marginal gains and having extra clustering in terms of explaining the variance is going down and down and down. But you can also use something like percentage of variance explained. So by percentage of variance explained, I kind of mean you've got your clustering, they all kind of shake and they move about, but then after, you know, assigning the clusters how much variance is remaining, this kind of arbitrary. You could choose something like, I don't know, depending how you go, 80% or something, 90%, depending on what your objectives are. It's quite judgmental. Also depends on how many columns there are. So visually, this only works if dimensionality is small, e.g. in all the lecture examples. So when I say dimensionality is small, I mean, you know, small number of features / columns. So here, there's 2 features. You can plot that very easily. If you have, you know, many real life data sets will have hundreds of columns, yeah, you can't, well, yeah, I don't know a way to plot that. Maybe 3, 4, 5 you can kind of get away with. You know, if you use color and time to get to the 5th dimension. So 3 is okay, you can do it 3D. And then, yeah, you can have like colors for the 4th dimension, and then you can do it over time for the 5th dimension, but that's just stretching it, right? You know, but really this, you know, visually, I guess you only look at a couple of dimensions at a time, but, you know, this is difficult if there are hundreds of columns. It's hard. But I feel like, you know, I feel like these two, I mean, I don't know what's the most common, but to me that feels like what should be the most common way to do it. And that's certainly how I've done it before. Let's see if I show elbow plot. Maybe it's not here. Where is elbow plot? Maybe I'm jumping around a bit too much. Yeah, it shows up again here. I'll jump to a bit later. All right, cool. Moving along. So one of the problems of k-means is that it can get stuck in a local minimum when it's trying to minimize intra-cluster distance. So you can see here. Okay. Yeah. So you can see here. This is an example of where you had a bit of bad luck. So these 2 stars are the initial clusters, and it's settled or converged here. And hopefully you can work out visually that it's not great clustering. I mean, really it should be something like, you know, here, you know, here's one cluster, and then here's another cluster. Basically like this. It should look more like this. I mean, hopefully you can see why. The problem is, you know, after this second iteration, you know, there's no further movement, at least based on these 2 centroids. Everything is closest already to the centroid it's been assigned to, the cluster it's been assigned to. So the way we get about doing this is a random restart. So what you can do is you can fit k-means a bunch of times, random initial, random initial centroids. And you take the minimum of that, or the one which minimizes the intra-cluster distance. This is a toy example which can demonstrate that. Here's another use case, image separation or segmentation. You can use it for compression as well. So if you take this original image and then you run k-means on it and just look at the two clusters that it belongs to, it'll look something like this. You can think of this kind of as a form of compression, right? And the more k's you have, the more clusters you have, the more definition you might have, right? But what it's saying is that, you know, we'll have two clusters, and when it's broken up, it'll look something like this. Okay. There's more examples here, but in the interest of time, I'm going to move on to your Gaussian mixture models. So this is another way of doing your clustering. What it effectively assumes is that you have, you know, your features, and it comes from some Gaussian distribution, right? Whether, you know, in this case, it's only got one feature, right? So you have some observations, and, you know, there's one feature, and you're trying to work out based on that one feature what cluster it came from, right? This Gaussian, your normal distribution, can be multivariate. So you can have, like, say, a 10-dimensional one. You have 10 features, and you assume it's a 10-dimensional multivariate Gaussian Gaussian distributed, right? So here you have, on the x-axis, here your features, right? And we have no target, remember, because it's unsupervised. And then this is our estimate. I mean, this is the our assumption. We assume that it came from two normal distributions, right? So here's one, and then here's the other. And then the task is based on all, but you know, but we don't know this. We don't know the distributions, and we don't know where it came from. And we've got to guess, make our best guess as to where it came from. Now, how it goes about doing it, can I show you an example? What's a simple way to explain this? Yeah, let's go here. Okay, sorry, it's an algorithm, but there's no other way to really go about it. So how this expectation maximization, oh, that's what K means. What happened to my Gaussian mixture model? Where is the K means? Okay. Oh, this is yeah. Okay. Yeah, sorry. Okay. Cool. So you fit your. Probably need another tab on this side. Just dang it. No. I don't understand why everyone likes Max. I still had it for almost 2 years. I still don't really get what the big deal about it is. I mean, yeah, I get it's got a terminal. That's kind of it, isn't it? I don't really understand. The keyboard really is not great. The current generation MacBook keyboard, I'm really not a fan. Okay. Let me just hop out of it. Can you just... Okay, sorry. Let me try and arrange my windows. Alright, you know what? I'm just gonna have just the one screen. This is not working. What happened to my... This isn't the one I want. Ugh. Sorry, let me just try and get this sorted. I apologize. Just trying to divide my screen into two. What the hell? Why is this not just... Alright, what's this? Where's the shortcut? Is it Command Control F? Command Control F. Okay, there we go. Alright, I've escaped. Okay, Command Control F. Okay. Alright, maybe I'll just use one screen full of it. This is just not great. Okay, sorry. I really would benefit from having... Why doesn't that work? Alright, maybe I'll just kind of just do it manually. Wait, where did we go? I'm not in full screen mode again. Command Control F. Okay, I'm not in full screen mode. This is here, and I want this one. Ugh. Again, I don't understand why everyone raves on about Mac OS. I don't get it. There's just so many things that just annoy me about it. Like every time I change from the trackpad to the mouse, I've got to change the scroll direction for some reason. And I've had this for 2 years. It's not like I'm not used to it. Or maybe I'm not. Okay, you know what? I'm just gonna have this one screen, and it's really slow. I don't know why. MacBook Pro i5, 16 gigs of RAM. I don't know why. Yeah, I'm running a virtual machine, sure, but it's not that bad, is it? Okay, all right. I'll just explain just using this one. Okay, cool. So what you do is you initialize. So in that previous example, right, we had in this example here, right, we had some sort of X value. So you will initialize it to something random. To a random data point within here. You initialize the two means of I guess the latent or hidden normal distributions, right? Okay. Now here, the EM algorithm, why is it called expectation maximization? Now, you go and calculate what you expect to be the clustering for each of your data points, right? So, I'll use this example. So you go through here, you're good if I had two screens. You go through here, and based on your initial guess of what the what distribution of but based on your initial guess of what the means are, you assign it to to one of the clusters. Okay, it's kind of like your k-means, isn't it? Except there's a distributional assumption. You assume it's Gaussian. Okay, now you do that, and you can see here. I don't know if you recognize this, but this is the normal distribution function. Hopefully, it looks a little bit familiar. Or maybe not. This formula here. That's this guy here, isn't it? Right? So you are calculating what you expect each data point to belong to clustering wise. Okay, and then you maximize. Now we say maximize because we use maximum likelihood we use MLE effectively to re-estimate the means of the normal distributions. Now the MLE estimator for a normal distribution's mean parameter is just a sample mean. So it's quite straightforward. You just take the sample mean of it all, and this repeat. You repeat and repeat and repeat. So look, this math might be a little confusing. Feel free to step through it. In your own time if you want to understand it, but effectively what's happening is, going back to the diagram, maybe I will doodle on it. I think it's a bit easier to understand. Okay, so what happened is you make some initial guess. Is this a good guess already? Probably is, yeah. You make some initial guess as to the what the means would be, right? So here, for example, over here, this will be your initial guess for, let's call it the first cluster, and I'm just going to put a 0 here just to know it's the initial guess. And then over here, this is a mu, a really ugly mu, by the way. And this is your initial guess, 0, index 0, for what the second mean should be. So, and these are random, right? So we assign these two randomly. So randomly choose a data point as the initial centroid, what means. Okay. Now that's your initial step, and that's what you initially do. And now we're going to do our E step, right? Now expectation step. What we will do is we will work out what I guess we expect each of the data points to belong to. Work out which cluster we expect each of our data points to belong to. Okay. Now initially we'll probably say, okay, all of these guys here up to here will be blue, and then we'll probably say all of these guys would be all of these guys would be purple, and then all of these guys would be blue. Okay, and after you do this, well, okay, cool, that's fine. Now let's use MLE, maximum likelihood estimation, to maximize to work out what to recalculate the mean of each of these Gaussian distributions. So maximization step, we use MLE to recalculate the means, to re-estimate the means of each cluster. So MLE here just means we use a sample mean of all the points in each cluster. Cool. So you can imagine, I mean, sample mean, the new one might be something like this, right? So we recalculate the mean, and it might be, yeah, somewhere like here, you know? I'm gonna say that. So now there's our new clustering. It's mu 1, mu 1, 1, and then we do the same thing for this clustering here. So maybe it's more like there's a couple of outliers here. I'm just gonna make it interesting, call it something like this, and then this will be our mu 1, 2. So it's our second clustering, and it's the first iteration. Okay, and then we recalculate our circles. So if we recalculate our circles, I mean, unfortunately, it's a pain, so I can't really easily shift this across. But you know, it might be, you know, some more like. Let me just get rid of. I need a bigger eraser, don't I? I made the eraser bigger. Yeah. Ah, wow. This sure is primitive. Okay, so then you recalculate, and you know, then the clustering might be something more like, you know, here, and you know, on this side might be like, actually, what I'm talking about, maybe, yeah, I mean, we'll just say this gets this one here. Cool, and then recalculate the mean, and you repeat this until some form of convergence. Now the interesting thing about all this is, even though I've kind of drawn circles like this as though we're hard clustering, it's really a soft clustering. Now why is it a soft clustering? Let me nuke this and pop it in here again. Why is it a soft clustering? You look at any of these data points here, right? And we have a probability of being in in each. You can work out some sort of probability of being in one or the other, right? And because the guy behind it, this is a probability distribution, right? So, you know, we can say, okay, we have a point. I mean, a point here is relatively not contentious, right? It's all the way out here. Almost certainly it's going to be coming from this cluster here, right? And on the flip side, you know, this point here is pretty uncontentious. It's probably going to, you know, come from this point here, right? But something more in the middle, here, this point here might be a little more contentious. And what you can do is, you know, you can read off both of them. Actually, maybe it's a point like here. What you can do is you can read off the probability distributions of both of these guys. So you can work out, you know, what the probability of here is, and you can also work out what the probability of here is. Because these little bell-shaped guys here, these are normal distributions, and you can look at the probability of this guy, and you can also look at the probability of this guy. And with the fancy maths, you can have a probability of being in each cluster. So it's a soft clustering, right? Now in practice, you would assign it just to whoever has the highest probability, but you know, this is what they're talking about, the concept of your hard and your soft clustering. Okay, that's your Gaussian mixture models and your EM algorithm applied to it. Cool. What else do we need to talk about? Yeah, so with your hierarchical clustering, okay, I'll talk about this, and then I'll talk about, and then you move on to the Jupyter notebooks. Running out of time. Okay, your hierarchical clustering algorithm. Let's run through this in a little bit. Okay, so this is the agglomerative bottom-up approach. So you start with your dissimilarity matrix, which gives you. I would really appreciate if I could cut the screen into two, because it's so much easier being able to like draw and stuff, and you know, to explain, or at least have two things. I'm gonna try this again. What do I want? Excel, don't I? Excel. Please work, please work, please work. Yay, it's working. Cool. Right. So we have your dissimilarity matrix, and it'll sum like this. I, J. And what you'll have is 1, 2, 3, 4. Let's say 3, and then 1, 2, 3. So your dissimilarity matrix, you know, you can measure it a variety of different ways. Let me just zoom in. You can measure it a variety of different ways. This is a dissimilarity matrix. We can use, say, like a distance, you know, as a measure of dissimilarity. And then this would be the distance between the two. Well, I mean, by definition, a distance function, you know, of an item, an element with itself, has to be 0. So these would be 0, and this might be, I don't know, say 2, 3.5, 2.1. And of course it has to be symmetrical, otherwise it doesn't really make any sense. Well, that's one of the definitions of a distance metric, have to be, I can't remember what the term is, but if you flip around the two arguments, it has to be the same. So distance of ij is equal to distance of ji, you get what I mean? So you have a distance matrix, looks something like this. You can make it fancy. Yeah, like this. So you know, red means they're further apart. So what you do is you will find the middle entry and merge your clusters. So in this case, you look at all these three. Actually, maybe I'll have more. Maybe I'll have more because it makes it a bit more interesting, doesn't it? And let's say, I don't know, 1.5, I don't know, 5, 2, I don't know. What's 0? Flip over. Cool. Why is that red as well? Cool. Right. So this is our distance matrix. We've got 4 guys. Okay, this is our dissimilarity matrix. We've got 4 elements, and if we're doing this bottom-up approach, what we'll do is we'll go, okay, cool. We want to merge the elements that are the most similar, right? Now, of course, you can't merge an element with itself. It's not really helpful, right? So ignoring all this, we'll go, okay, what is the smallest? It's the most green thing, right? Again, ignoring the diagonal. So it'd be these two, wouldn't it? So what you would do is, where did that guy go? Here we go. Yeah, you probably wanna merge these two together, right? And then you'd form. I don't want to recalculate the dissimilarity matrix, but you merge these two together, and you know, I'm just gonna kind of make it up, but you're gonna have like 3, 4 here, say 3, 4. I should make that up. Right, and this has got. Damn it, Mac. Okay, that's gone, and this is gone, right? And these two distance metrics would be the same, but this might be someone else. I'm just gonna make something up. Okay, right, and I'll explain how you recalculate in a little bit. Okay, and then you so you find the minimal entry, and then you merge the clusters as we have done. Okay. Then we update D by deleting the column and the row and adding the new column and the row. So we've done that. So we've deleted column 4 and row 4. Sorry, column 4 and row 4, and then we merge these two to get 3, 4 as a new cluster. And then we revise the distance matrix. And then there's a couple different ways to recalculate it, but I'm just gonna make it up and call it 2.5. And you kind of do the same thing, right? And you look here and you're like, what's the smallest one? Well, it's 2, 3, 4, isn't it? So now we want to merge these two, and we have this, right? And we just recalculate. Oh, yeah, I'm just gonna make it up. 1.5, and then and then from this you can actually create a Dendogram. But hopefully you get the idea of how this kind of works. Cool. Right now, when I sort of made up these numbers of 2.5 and 1.5, when I made up the numbers where of the distance after you merge it, there's a couple of different ways you can calculate it, and it's here. You have your single, your complete, and your average. Now, what it really means is, I think, ignore the formula. I think it's easier to see in the diagram. Now, your single linkage really just looks at the minimum distance between your two clusters. Your complete linkage looks at the maximum, or the furthest of any 2 points away from each other, from the two clusters, right? Mm-hmm. Now, of course, you can actually look at the flip side, because here the smallest two, the closest two points in each of these clusters are also the most similar. So you can think of this as either minimizing the distance or maximizing the similarity. Likewise, you can think of your complete linkage as maximizing the maximum distance away from each other, or you can think of it as the minimum similarity away from the minimum similarity between any 2 points from the two clusters. Now, your average links just averages it all out. There's a couple of different ways to average it. I'm not going to go into that. Another form of averaging is, so this is kind of a simple average of all the pairwise distances between the points in the clusters. There's also the centroid distance, where you calculate a centroid, like as I was saying before. You look at each component, so you look at each dimension one by one, say x1, x2, and you average out all x1s, x2s of all the points in each cluster, and that's your centroid. So it may not actually be a real point. Cool. I really have to go to the Jupyter notebook now, because I'm running out of time as usual. Oh, but the elbow plot, this is interesting. So the elbow plot, this is one of the ways you can choose the number of clusters you want, and this applies to a variety of different algorithms. So I've actually been using this exact thing for PCA at work. So yeah, you can it's kind of judgmental, kind of subjective, but the feel you want, you can measure this a variety of different ways. So actually, on the y-axis, I find it more intuitive to view the percentage of total variance explained. So you can kind of think of it as almost not a compression ratio, but you can kind of think of it as the amount of loss you get, when you're compressing the data in a ways. So if you could have say scree plot. They have eigenvalues though. What's wrong with the percentage of? Oh, percentage of variance. PCA percentage variance. Okay, I mean, to me, something like this is, yeah. I mean, you can look at it this way, and you can kind of just think to yourself, okay. And they say elbow because it's just, you think of it as kind of an elbow where it points out. The concept here is you want to find the point where it's getting quite marginal in terms of the gain. So every cluster you add makes the model a bit more complex and adds more features, but adds also some more, I guess, explanatory power in terms of the variance within whatever you're trying to reduce the dimensionality of. You can kind of think, okay, look, the point when it starts to flatten out, when you think it's getting a bit marginal in terms of your return and explanatory power on, I guess, number of features you're adding. And you can say, okay, maybe this point here, or maybe even something like this. What I find more intuitive is if you look at something like this. This is the same sort of thing, but it's sort of a percentage base. You can think of it as the percentage. So this is flipped around. This is percentage of variance explained. You can look at 1 minus this, and this is the percentage of variance unexplained, and look like the elbow plot that you're seeing. So it's really just two sides of the same coin. You can look at 1 minus the same thing. So you look at this, and you can kind of find the elbow. You can be like, okay, maybe around here, or maybe even there. But this is good as well because it gives you a feel of how much of the data you're losing, how much information you're losing. I mean, if you choose here, you really lose it. You can think of it as losing maybe 13.5% of all the information that was in the original data set. So I like this view, the percentage of variance explained. That's another view you can look at. Cool, let's go to Jupyter, but I'm over time as usual. Running out of time as usual. Right, okay. The first thing that they go through is the PCA. So they generate a, I didn't talk about PCA, did I? Oh, I guess we'll talk about it here. So they generate a random correlated data set here, which looks like this. So you can think of this as feature 1 on the x-axis and feature 2 on the vertical on the y-axis. Now, what PCA does is PCA, you can think of it as it tries to project your data set into some new dimensions, right? Which can explain most of the variance within your data set, right? So it tries to find new dimensions, which are themselves linear combinations of the existing ones that can explain most of the variance within your data set. So I think the easiest way to sort of understand is to look at the diagram. So actually this guy here, this one. So here, this long line here, this is the first principal component, and this is the second one. So what it does is what the PCA algorithm will do is it will try and find a vector which is spin around and try and find a vector which can capture most of the variance. Now this vector will be a linear combination of all your features. So for the first, when they're trying to find the first principal component, what we'll do is it's centered around 0, and this vector you can imagine it's spinning around, rotating around, and trying to find the dimension which captures most of the variance. You can see this captures most of the variance, right? You can see it, all this goes from here to there. Using that one dimension, it captures most of it. This principal component is made up of largely x1 with a bit of x2. So maybe like it's made up of, I don't know, 2.5 x1 plus 0.9 x2. It should say somewhere here, shouldn't it? Here it is. Yeah. So it's I mean, these have been rescaled, but it's effectively mostly x1 with a touch of x2. So mostly x1 with a touch of x2. And the next one is just what is this? These are the components. Yeah, I mean, these are orthogonal. Yeah, so in this example, because we've only got 2 dimensions, it's your second your second principal component doesn't really have much choice. It kind of has to be that. But it becomes a bit more interesting when there's more than two dimensions, because then the second vector has to spin around in a way that's orthogonal. Oh, that's right. Principal components are orthogonal. That's another cool thing about it, which makes them useful because they are uncorrelated. So your orthogonal, your features which are orthogonal will be uncorrelated, which is very handy from a modeling point of view. But you can imagine you have this principal component here. If you choose something orthogonal, you don't really have a choice. I mean, you could go the other side, but you know, it's the same thing, isn't it? It's when you take the negative of that, it's the same. It's just flipped around. Right. So we have a random data set. Okay, and then we use sklearn here. It's got a nice little PCA package. You initialize your PCA object, and here we set the number of components to 2, and we fit it. Right. And the cool thing is, once we fit it, we can actually break apart the components. So your first principal component is the one which explains most of the variance. And what we can do is, once you fit your PCA, you can access the explain variance attribute. And in this case, it says 76 of the variation in the data, 76% of the variation in the data is explained by the first principal component, which is a vector of mostly your first feature with a bit of the second feature. And you can draw it out here, right? So it's mostly, you can see, you know, it's mostly made up of this first feature with a bit of the second feature. So the reason why this is like this is these have been rescaled, whereas this hasn't. So it's not exactly going to be 2 point something. Cool. Yeah, so you can use PCAs for dimensionality reduction. So you, for example, in this toy data set, you can boil down this data set into just this one dimension, which will actually capture most of the variation within that data set. Now, to give you a real life example, what you can think of is, let's say on the x-axis you have something like height. On the y-axis you have something like weight. So maybe something like, width, height and width, right? Maybe we'll go height and then say, I don't know, let's say waist circumference measurements, you know, some sort of measurement of breadth, right, of a human, right? Now, you can imagine those two constructs are highly correlated, right? Someone taller is likely going to be a bit wider, broader, maybe have a, you know, bigger waist. That all kind of makes sense. Now, this first principal component, one way to interpret it is it's measuring size. The underlying construct both of these things are measuring is size, right? So instead of thinking about height and weight, we can think about size, you know, and this has, you know, compressed our data set. Instead of having a field for weight and a field for waist circumference measurement, we have size, which is the underlying construct that maybe we're trying to capture, maybe that we care about, right? So here's an example here, the PCA for applied to the MNIST handwriting recognition dataset, the famous dataset. Now you summon the MNIST dataset, and have a look at the shape here. So the original one is has 64 columns because it's an 8x8 pixels. So you have 64, and then each one of the pixels is considered a feature, right? And then we use PCA, and we try and distill this down into two principal components, which hopefully can explain as much of the variance as possible. Now I printed out here the two principal components. They're made up of a linear combination of all 64 pixels, all right? And it's interesting here because these two principal components don't actually explain all that much of the data's variance. So the first one you get about 15%, and the second one you get 14%. But the interesting thing is, even just using those two principal components, you can see here that those two actually can do a pretty good job, even though. So I have to separate two things. So when I say what it's explaining, I'm saying it's explaining the variance in the data. So this is ignoring the target. So this is unsupervised learning, right? Now, this is separate from say explaining. This is different to say explaining the variance in terms of the target. Now here we look at the target, which if we put the target back on, really it's what number it is, right? You know, we're trying to recognize the number. You know, what is the number? That's a target. That's a response. You can actually see kind of some clusters here, right? Which tells me that if I were to build a prediction model right, and I just use these PCAs and just 2, it could probably do an okay job, because just what you could do is, right, you could run your PCA, right, and you have here, and you can visually see there's some clusters here, right? Or maybe then you run maybe here then you run, say, I don't know, maybe even run k-means on this, or some sort of k nearest neighbors, right? Some sort of centroid clustering, right? And then you associate it back to the numbers that you have, right? So maybe I'd even do k nearest neighbors, right? Because you run your PCA and you have your 2 dimensions, and if you do k nearest neighbors on any of these, you could probably get an okay result, right? So if you do k nearest neighbors, it would segment it out. You'd have segment this guy out. You'd have decision boundaries all along here. It'd probably get confused for the digit 8 and what is that? Number 8 and 9, which kind of makes sense. Actually, that actually makes a lot of intuitive sense, because 9 and 8 kind of look similar. Even here, they kind of look similar-ish. But yeah, you could then feed this into classification algorithms, say k nearest neighbors or something else. Right. Here's our scree plot. Oh, here we go. This is to me, this is more intuitive than if you just have mean square error, because it's a sort of percent. You can kind of get a feel of how much information you've lost. And this is an elbow plot, and the scree plot's something else related, which is very similar to this. And you might choose something like here. Maybe that's the elbow, right? That's when you start getting diminishing returns. Or even if not, even if you choose, say 40, that captures, even if you choose 40 principal components, that captures almost all of the variation. That's doing a pretty good job, right? And you don't even need the last 20. You can also use your PCA as some form of noise filtering, right? Here is your original handwriting data set. You artificially apply some noise to it. Then you run PCA onto it. There's a transformation. Yeah, here we go. We run our PCA on it. Okay. And here we only use 12, right? I think it's 12. What means that there's 12 components, right? And then you fit it back onto data sets, and you can see it's cleaned up the noise quite a bit, which is nice. Another freakier use of your PCA is what they say is your what they call eigenfaces. Each one of those principal components is effectively an eigenvector. So what you can do is here's a data set built into sklearn, right? And then you fit your PCA to it. In this case, 150 principal components. Now, what you can do is you can look at each of these. You can look at each of the principal components. And the interpretation here is that the principal component is trying to capture as much of the variance in the data as possible. So you could kind of think of each of those principal components as kind of ignoring image data. In a tabular data, it'll be kind of trying to capture some sort of underlying construct. So my example before was say size, right? If you had say census data, right? Some of the underlying constructs could be things like socioeconomic status, right? If you had things like vehicle data, types of vehicles, it could be capturing, like underlying constructs like how big the vehicle is, how powerful it is it an expensive vehicle, just like basic constructs, In this case, it's capturing things like the first couple could be, say, the lighting. Some might be the kind of nose that you have, and the facial structure, the kind of mouth. That's another way to kind of interpret it. All right, here's our scree plot. Okay, and here what's happening here is it's looking at the you can kind of use it to almost compress or simplify your data set. So here's a full input, and running it through your PCA and only using 150 components, you get you can see how you've lost some information here, but it seems to capture the general gist of the shape. The broad strokes are kind of there. And it's capturing 90% of the variance, and this can be used for a variety of different ways. Image processing, one of the challenges could be that there's far too many features. Surely far too many. If you look at the number of pixels, if you have say 1,000 by 1,000 pixel image, that's 1 million features right there. could be way too many, right? And obviously there's other ways to deal with it. We talked about a convolutional neural networks, which tries to deal with that dimensionality problem by only having locally connected layers within your neural network. Here's another way to reduce dimensionality and sort of compress a data set. Cool. The other way, another way of clustering that we'll look at is your k-means. Okay, so here's just generating a random data set. Okay, so what we do here is we just use a k-means implementation from sklearn. It's fairly easy, self-explanatory to use, and did quite well. Now, here it asks, you might be wondering how it works, and we talked a bit about it before, and we looked at the pseudo code. But actually, let's have a look at some real code and see how it works. Where is our k-means implementation? Here it is. Okay, here's our k-means implementation. Now, what will be helpful is if I pulled the algorithm on one side. Here. Nope. Alright, I'm not going to try with this. I'm just going to do something with this screen. It's just not going to work. Okay. Right. So, step one, hopefully you recall from your k-means algorithm. Sorry, I'm just having some screen issues. Here we go. Okay. So you initialize your means to you initialize your centroids to a random point within the data set. Choose something random. And then you have your two steps, your EM, your expectation step. You work out what you expect each of the data points to belong to in terms of their clusters. And then you maximize, right? You I guess in the case of the Gaussian mixture models, you're using MLE. But here we're recalculating and finding the new centroids, and you repeat until it converges. In other words, the clustering doesn't change. Now, of course, this is a good one. I mean, here we've chosen 4 because visually we look at it and we think, okay, 4 feels about right. Now, one of the problems of your EM algorithm or your k-means algorithm is, you can get stuck in a local minima. Here, it is clearly a local minima it's stuck in. There's 4 clusters, but it's not great. So what we want to do is we want to do a few random restarts a couple of times. Is it here? No, it's not here. But what you want to do is you effectively want to do a few random restarts. So you run your clustering algorithm a few times, and then you choose a one either visually or maybe you look at, say, the total intra-cluster variation. You choose the one which minimizes it. That should be your best one, right? Okay, what else? Okay, and we can do k-means. We can do the same exercise on that handwriting recognition data set. So here it is, your 8x8, 64 pixels. Where's the k-means? Have I run k-means? Here we go. Yeah. Okay, cool. So we've run k-means on this data set, and what we can look at is we can look at the centroids. Now the centroids here. So the structure of this MNIST data set is something like this. So you have observation, so that's an index, and you have, like, say, pixel 1 and then pixel 2 and then the number might actually be 1, 2, 10, 9. So your data set might look something like this. Your MNIST data set. Okay. And then each one is a number, right? And then the features are the pixel intensity. I'm just gonna make it up, right? How is it moving? Come back. Jeez. Cool. Right, so this is kind of what our MNIST data set would look like, and obviously we'll just, keep going on to however many. And each one is a pixel intensity. Now you run your k-means on this, and then you're going to have, let's say you run k-means with k equals to say a 10, because there's 10 digits, not 9. So I should really this would make more sense. There we go, cool. Yeah, here's a random data set, right? Now, the centroid of each one, you can imagine, could be kind of interpreted as a number, couldn't it? It's the average pixel intensity for everyone in, hopefully, if the clustering is any good, it'll be the average pixel intensity, let's say for the number 6, and let's say the clustering is good. So most of those data points are actually number 6. Now you take the average pixel intensity for all 64 pixels, and that's the centroid. And then you plot it here, and this is what it kind of looks like. And it kind of makes sense, right? You get 0, there's a 4, 3, maybe it's not the best, but 4, 3, 5, 9, 7, 6, 2. And it's getting confused with some of them. I don't know what that is. What do we say? 0, 1, 2, 3, 4, 5, 6, 7. Maybe there's an 8, 9, and that's a 1. Maybe 1, 8, 9. I don't know. It's not the best clustering here, but hopefully you get the gist, right? This is how the data set looks like. You run k-means on it. The centroid can be interpreted as the average pixel intensity for every pixel for each cluster, which hopefully aligns nicely to each of these numbers. Cool. And that's kind of it. I mean, this you can look at your own time. I don't think it's examinable really in the course. There's some other clustering methods. I mean, like PCA and k-means, I think they're pretty good. I mean, you can explore other ones, but I mean, as I said in the lecture, I mean, it's not clear cut if it's any of these more sophisticated ones are that much better in general. I mean, obviously there could be some use cases where these are great, but k-means and PCA, yeah, they seem pretty good. Cool. So that was 9417. It was lovely, tutoring you guys. Unfortunately, I would love to do this in person. Unfortunately, it had to be online, which is a bit of a shame. But hopefully this all clears up, and we can all, go back to uni in person. I think it's much better learning that way. But thanks, guys. If you haven't, please fill in the My Experience survey. That'll be much appreciated. And good luck for your assignment and the finals. Okay. All right. Have a good one. You guys stay safe.